will be good. Yeah, that's exactly what I'm going to do first, Nick, because I'm going to talk about how to find the first pedal. So for cosine, it's always really easy. For cosine, the first pedal should always be at an angle of theta equals 0, because when you take the cosine of 0, you get 1, which is the largest that cosine can ever be. So that's always going to be the furthest out for one of the pedals, right? But for sine, it's a little bit different. It's sine, the largest value for sine is also 1, but that occurs at whenever the angle is pi over 2. So we're going to have to set our angle, 5 theta or 2 theta in this case, equal to pi over 2, and figure out where that first pedal starts. So we're going to do that right now with we'll start with the 3 cosine 3 theta one. So since this is a cosine one, we know that the first pedal should start at theta equals 0, because if theta equals 0, then the cosine of 3 theta is equal to 1, and we'll end up with an R value of 3. So that's our first pedal, is going to be that far out. How many pedals are there going to be for this one? Should be, I'm sure, I guess I can open up this chat so I can see. Yeah, okay, good. So we should have 3 pedals on it. It's way too big. All right, 3 pedals for this one, because it's 3 theta. It's an odd number, so it should have the same number of pedals, which means 3 evenly spaced out pedals across the 2 pi. So if the first one's at 0, the next one should be at 0 plus the full 2 pi divided by how many there are. So the next one should be at 2 pi over 3. So we should be out 3 units at 2 pi over 3. And then the next one should be at that second pedal, 2 pi over 3, plus another 2 pi over 3. So that one should be at 4 pi over 3. And, now, if you're looking to get just a nice, perfect, exact, thing, you can plug in these points, like plug in pi over 12, and you 3 times pi over 12 is going to give you pi over 4. Cosine pi over 4 is going to be root 2 over 2, and you're going to have 3 root 2 over 2. You can figure out about what that is. But for right now, I don't need you to get an exact value for those. If you need to, I'm sure you can. Just draw yourself 3 nice little pedals here, and you got a rose curve. Everyone good with that? Any issues with that? Okay, cool. So we'll go on to our next one here. Maybe. There we go. So we got 5 cosine 4 theta. I got another cosine. I hope I put a sine one here. If not, we'll throw an extra sine one in here. So we got 5 cosine 4 theta. So once again, this one's going to start out at 0 because it's cosine function. So we know that it's going to be 5 units out at 0. And how many pedals should this one have?
8.
Yep, should have 8. So they're going to be evenly spaced out across the 2 pi radians. So 2 pi over 8, or every pi over 4, we're going to be out to another full pedal. So there should be one at pi over 4, pi over 2, 3 pi over 4, pi, and so on. So we should have 8 different pedals. If we want to figure out exactly the value of what it is at pi over 12, put in pi over 12. That gives us 4 pi over 12 or pi over 3. What's the cosine of pi over 3? Yeah, it's a half. Thank you, Nick. So cosine of pi over 3 is a half, and 5 halves. So we should be right out at 2.5 at the pi over 12. These are always going to be symmetric. So pi over 12 and 23 pi over 12, it should be the same. And same thing here, pi over 6, it should be the same, and pi over 3, 5 pi over 12, 7 pi over 12, and so on. So if we wanted to make this, look real nice, which drawing on my laptop screen, I'm not going to be able to make it look real nice, but there's one pedal. I promise if we were in the classroom and I was drawing on the board, these would look really nice. I'm sure you all believe that. But basically, it's going to look like that. Easy enough? Any issues with that? I don't have a sine one here. All right, so I'm gonna put a new page in here so we can do one with the sine, because I think that's important. Ignore that says r squared equals 4 sine 2 theta. We're going to just we're going to call that r equals 4 sine 2 theta now. We'll do r squared in a second because that's going to be a different one. So if we got r equals 4 sine 2 theta, we need to figure out where the first petal starts. So we know that the sine of, we want the sine of 2 theta to be at its maximum, right? So we want, we need 2 theta to equal pi over 2, because that's when sine's at its max is at pi over 2. So that gives us theta is equal to pi over 4. So our first petal will be out 4 units because of this a value out in front at pi over 4. So 1, 2, 3, 4 out there at pi over 4. How many petals does this one have? 4, exactly. So evenly spaced out across the 2 pi, 4 different petals. That means that every pi over 2, we should get a new petal. So from pi over 4 to 3 pi over 4 should be a new petal, 3 pi over 4 to 5 pi over 4, and over at 7 pi over 4. So far good? Hopefully. And then if we want to figure out the exact values of what these are, we can, we can plot the little points at 5 pi over 12 and pi over 3 and see how big these petals look. But for our purposes for now, not super necessary. They're going to look nice and symmetric. Pretend that those look perfectly exactly the same. Good or no? Nick, does that help you with figuring out where that first petal is and then how they're spaced?
Yes, thank you.
Yeah, no problem. All right, cool. So let's move on to another type of polar curve that we want to know a little bit about. These ones are not put in the form r equals. These ones are r squared equals 4 sine 2 theta. And or a sine 2 theta. There are always going to be 2 thetas in there, and it's always going to be an r squared on the left. And then this a value here, that value out in front, is going to change the length of these petals, because they're still going to be similar to rose curves, but a little bit different. Let's plot a couple of points this time, actually. So let's plug in theta equals 0 and see what happens. So if you plug in theta equals 0, what do you get? What does r equal?
0.
0, exactly. So we're sitting there at the pole, right? Let's say we plug in theta equals pi over 12. What is r going to equal?
Square root 2.
Square root 2, right? So we're going to have square root 2 here, which is about what, 1.4, right? Put that there. What if we put in pi over 6? What's r going to equal? It's going to get a little bit messier now. It's going to be like the square root of like 2 root 3 or something like that. Right? Sine of 2 pi over 6 is sine of pi over 3. Sine of pi over 3 is root 3 over 2. 4 root 3 over 2 is 2 root 3, and we got to square root it. So it's the square root of 2 root 3, unless I've lost my mind, which is possible. What's that approximate out to be? Somebody's got a calculator in front of them. 1.7, 1.8, something like that. 1.86. Perfect. Thanks, Nick. All right, and then at pi over 4, what's r going to be? Pi over 4, that's going to become pi over 2. Sine of pi over 2 is 1, right? So with square roots that, we're going to end up with r equals 2. And one would probably guess, since when we had r equals 4 sine 2 theta, the max we went out was 4. If we have r squared equals 4 sine 2 theta, the max we're probably going to go out is the square root of 4. So the max we're going to go out is 2. And this is going to mirror itself on the way back down in towards the pole. So it's going to look just the same. So we got something like this on this side here. Then what about when we plug in, let's say 7 pi over 12? What happens there?
R doesn't exist.
Yeah, r doesn't exist. Why doesn't r exist?
Because you have a square root of -2.
Right. We end up with the -2 in there, and we get the square root of -2. So we can't take the square of the negative. So these values that are supposed to be coming out from 7 pi over 12, which would normally be giving us this pedal in the second quadrant, aren't going to exist at all. All right. So we got nothing there. So when are we going to end up getting values again? Suppose we plug in 13 pi over 12. Is that going to give us something? When I double 13 pi over 12, what does that give me? It gives me 13 pi over, gives you what, 13 pi over 6? Right, 13 pi over 6 is actually an angle in the first quadrant, so you're going to get positive values for sine again, right? So 13 pi over 6, sine of that is the same as the sine of pi over 6, which is going to give you that same √2 value. So you're going to be back out here with a pedal that looks just the same. I don't know what happened there, but and what's going to happen when you're in the fourth quadrant, putting in angles in the fourth quadrant?
They don't exist.
Yeah, they're also not going to exist. And so we're just going to end up with these two pedals. So we're going to get this like figure 8 infinity kind of looking thing, where the furthest out that we end up going is the square root of that a value out in front. And anybody know what this one's called? It's not a rose curve. It's not a limestone. Anybody know what these ones are called? It's not called a figure 8. Lemniscate. Ah, look at that. And Nick even like spelled it right and everything. Excellent. Probably because you looked at the notes already, huh? These are called lemniscates. And yeah, here's the info about lemniscates. So we'll go back and graph the cosine one also, but easy enough to see. Sine ones are always going to be at a diagonal, where that first pedal in the first quadrant goes out to pi over 4. And the cosine ones are always going to be across the polar axis, where they're just literally look just like an infinity symbol. Easy enough. Furthest out they go is always the square root of that value that's out in front. There's always just going to be two pedals. And these will show up every once in a while. Every once in a while, they put one of these on the AP test with finding the area inside of it or figuring out the length of the curve itself, something like that. Anybody have any questions on that? So this one, r squared equals 4 cosine 2 theta. How far out should I go? For my first pedal, 2 units, and 2 units on this side as well. I'm not going to bother to plot the points. It's going to look just the same. It's just going to be that nice little infinity symbol, nice little lemniscate there. Good? Everyone's good with that? Cool. All right. One last little one to talk about. What do you think this one's going to do? R equals theta. Any thoughts on that? Yeah, Luke, that's right. It's going to be a spiral. Specifically, this is called the Spiral of Archimedes. And kind of cool. Just throw out your values there. Yeah, so these will, it comes out at the golden ratio. That's exactly right. Yeah, that is 100% true. So I don't know exactly what pi over 12 is off the top of my head, but it's small. It's about a quarter, something like that. Pi over 4, we'll call it like 3/4-ish. That's going to be just a little bit above 1 at pi over 3. And out at pi, 1, 2, 3 and a bit. And you can see it's just going to keep spiraling out here. Something like that. That's not perfect, but it's going to spiral out. If you, you can change the theta, make it a half a theta or a 2 theta if you want to make it a tighter spiral or a wider spiral. If you want to play around with those in Desmos and kind of see what they do, that's fine. But that's about it. That's the basics of polar coordinates. Anybody have any questions on polar coordinate stuff?
Can you explain how you got the points for the spiral?
Yeah, I mean, r is equal to theta. So if theta is pi over 12, I just ballparked it by calling pi 3. 3/12 is a quarter. So I just a little bit out there, went out a fourth at pi over 12. At pi over 4, I said that's about 3/4. So at theta equals pi over 4, r equals pi over 4, which is about 3/4. At pi over 3, when theta is pi over 3, r is pi over 3, which means it's just a little bit more than 1. At pi, it's just a little bit more than 3, and so on. Does that make sense?
Yeah, thank you.
Mm-hmm. All right. So, any other questions on polar?
For the lemniscates, or the whatever they're called, the last one, what does the a squared in the equation mean?
So normally they write this as a squared. It's just telling us that we go out a. So the value that's there is the square of however far we go out. So if we were writing the equation of this particular one with the cosine here, since we've gone out, it looks like 5 units, this would be r squared equals 25 cosine 2 theta. Because we go out 5, the square root of the number here. So this one, I can't tell the thing on the graph, but does that make sense? Or no?
Yes, that does.
Okay, cool. Any other questions on anything with any of the polar stuff? The big thing you're going to want to be able to do with polar graphs is you're going to want to be able to graph the lemmastones really well, especially when we get to doing all the area stuff. Because when we do integrals and we do our areas under the curve, we're going to be finding the areas within a bunch of different lemmastones, finding things like the area of just the inner loop of a lemmasone, or the outer loop minus the inner loop, that kind of stuff. So you're gonna need to know what they sort of look like. But other than that, we won't do a ton with polar stuff other than derivatives and integrals. We're not gonna do a lot of crazy stuff with it. So none of it gets too bad. All right, did the parametric stuff show up just now or no? Or do I need to reshare my screen?
Did you need to reshare your screen?
Okay. Yeah, I can see it on mine, but I can't tell if it's on yours. Now is it there?
Yes.
Okay, cool. So I don't know, the school was having some issue with I don't know if it was Google or if it was the district Google Drive stuff or what, but I got this up only a couple minutes ago because it wasn't working last night. But I don't know if maybe you saw it, maybe you didn't see it in advance, but we're going to talk a little bit about parametric. How many of you guys have done anything with parametric equations before? Anybody? I can't see any of your faces, so if you're just nodding your head, I have no clue. But I feel like in AIM 3, you did a little bit with parametric, is that right? Yeah, that's what I thought, okay. But most of you guys didn't do honors pre-cal, which doesn't really do parametric much anyway. Anyway, parametric equations are pretty straightforward. There's going to be a couple of different types of them that I'm going to want you to be familiar with, but most of them you can just, you'll just be able to plot the points by plugging in different t values given the restrictions I give you on t. So t in all of these parametric functions is what we call a parameter. And both the x and the y variables depend on t. So rather than, in a regular Cartesian equation, the y value depends on the x value, right? X is independent and y is the dependent variable. Well, here, both x and y are going to depend on a third variable, which usually is t. We may make it other things. We might make it theta sometimes, or who knows what horrible letters I might choose for it. But generally, it's going to be t, and we call t the parameter. So we'll restrict our parameter to some set of values, or we might say that t is for all real numbers. In this first one we're looking at, we're going to say t is greater than or equal to 0. So for values of t, and often this is used for time and particles moving in a plane, and that's how we're mostly going to use it. So we're going to say for time greater than or equal to 0, the x coordinate of some particle is equal to the square root of t, and the y coordinate of that particle is equal to t. Does that make sense? Or no? Okay, so let's say t is equal to 0. If t is equal to 0, what is the x value? Should be 0. And what should the y value be? Should also be 0. So we're going to start here at the origin. This is just a regular xy plane. We're going to graph these on a regular xy plane. What about when t is 1? What should our point be?
One comma one.
1, 1. Yep, easy enough. What about when t is 2?
Square root of 2, 2.
Okay, should end up with the square root of 2 comma 2, which is a little bit of a pain. 1.4 and 2, right? What might be an easier value to plug in here? Like t equals
4.
4? What's that going to give us? 2 comma 4, right? And so on, right? We can probably have a general idea of what this is starting to look like. What is this starting to look like? Anybody have an idea of what that's starting to look like? Yeah, it's starting to look at least like a parabola, exactly. Not a full parabola, only half of a parabola, right? If we put in, let's say t equals 9, that's the next nice easy one, right? That gives us the point 3 comma 9. This is just the right-hand half of a parabola, right? How could we show that this is true? How could we convert this into a rectangular coordinates? Anybody have an idea of how we could do that?
Put one of the equations in like terms of t, and then substitute that into the other equation.
Okay, so we've got one already here in terms of t. Y equals t, right? And so if we do that, that means that I can replace this t with just a y. So we got x equals, well, that's not a square root. Square root y. And if we square both sides, we end up with y equals x squared, right? And we do need to clarify that this is y equals x squared for x greater than or equal to 0, right? want to clarify that because we're only looking at t values that are positive. The t values are, we can't have any t values that are negative because we can't square root, and we can't square root that negative. So we're always going to get positive values for x because we're always taking a principal square root there. So that's our restriction on the x values. Does that make sense? I'll assume based on the silence that that makes sense. Let's look at another one. What do you guys think this one's going to look like? Anybody have an idea of what they think this one's going to look like? Yep, that's exactly right, Ryan. It's going to look like a circle. So we could plot some points here. What's another way we could determine that this looks like a circle?
Solving one of the equations for C.
I have no idea what you just said because you were cutting in and out the whole time. I'm guessing it sounded sort of like solving one of them for t and substituting in, but that's going to be a little bit more difficult with this one, I think, because we're going to end up with something like x over 2 and then the inverse cosine of that, which is a little bit of a pain. But maybe we could use some of the rules about trig functions and how they operate to sort of combine these two things together. Rather than specifically solving for t, we can find a way to get rid of t in a different way. Anybody see a way to try and do that? Okay, yeah, if we square both sides of this, or square both of the equations, this one's going to be x squared equals 4 cosine squared t, and this one's going to be y squared equals 4 sine squared t. And what good does that do us, Luke? What can we do now? Yep, if we add them together, add the x squared and the y squared, that should give us 4 cosine squared t plus 4 sine squared t. And easy enough, we'll take out the 4 from the left-hand side, right? And cosine squared t plus sine squared t is going to cancel out for us. It becomes just a 1, so we just end up with x squared plus y squared equals 4. So we can just say that this is a circle centered at the origin with a radius of 2. So I'll write that out here. Circle centered with my chicken scratch on the laptop screen. The radius equal to 2. So we'll want to recognize that anytime we've got x equals, let's say a cosine t and y equals a sine t, or vice versa, the sine can be with the x and the cosine can be with the y. It doesn't really matter. As long as these two values here are the same, it's always going to be a circle. And I'm going to pop open Desmos here real quick, just so you guys can see. You guys see Desmos now? Yeah, okay, cool. So the way that you want to put these into Desmos to do parametric functions, because you may need to graph parametric functions in Desmos just to get an idea of what they look like, just to save you some time. You can also do it on your graphing calculator, but Desmos is a lot nicer. Put the x coordinate and the y coordinate in parentheses as if they were an ordered pair. So 2 cosine t to sine t. And as soon as you do that, it's going to put in a range for the t values that you want. So we want 0 to 2 pi. We can see that that's going to be a circle. Okay. Everyone good there? Suppose I change them both to 3s. It's just going to move it out, give it a radius of 3. You probably noted as I was going through there, what happens if I change just one of these? Suppose I turn the cosine t1, that's my x coordinate, into a 5. It's going to push out my x coordinates so that they go out to 5, whereas my y coordinates are still going to go only up to 3. It's going to turn it into what? What is this? Yeah, it's an ellipse. So it's going to turn it into an ellipse. So that's going to be something else that we're going to want to be aware of. We want to kind of play around with this. If you make, turn this one into a 2, it's going to make the ellipse have its major axis on the y-axis, right? And the minor axis is the x-axis. If I make the value in front of the x coordinate larger, it's going to be the opposite way. What do you think is going to happen if I flip the sine and the cosine around on this? If I make this 4 sine t, 3 cosine t. Same thing, right? Doesn't matter at all. Okay? Same ellipse. Doesn't change it one bit. As soon as I flip one of these, though, it's going to, change the major and the minor axis. We're all familiar with what an ellipse's form is in standard, regular, like rectangular coordinates, I hope, or no? How familiar with that are we? Hopefully very familiar, but if not, this is what it should look like. This is your standard form for an ellipse. You should know this also. X squared over a squared plus y squared over b squared equals 1. And tells us where our major axis and our minor axis are, and which axis they're over, and which one's the, whether it's the horizontal major or the vertical major axis, depending on if the value under the x or the value under the y is larger. Does that all look familiar from stuff you've done before, or is that new to people? Familiar, good, I like that, familiar. Thank you, Nick. All right, so then my question is, how are we going to turn, let's say this ellipse, because this is an ellipse, 3 cosine t and 4 sine t, how are we going to turn this into the standard rectangular coordinates of an ellipse? Any ideas on that? Similar process, but it's not exactly the same as we did for the circle. Divide first, so you're saying you want to take the x equals 3 cosine t and make it x over 3 equals cosine t, Adrian? Yep, that's exactly right. And the reason we decide to do it this way is because now when I square both sides of this, I've already got the denominators in with the x's and the y's like I need in the ellipse formula. And I'm just going to have, shouldn't have made that a sine squared t yet. I'm just going to have a cosine squared t plus a sine squared t on the other side, which is going to come together to give me 1, which is what we need for the ellipse equation. So we'll turn this into x squared over 9 equals cosine squared t, and y squared over 16 equals sine squared t, and put them together, and you got x squared over 9 plus y squared over 16 equals 1. And we should be able to tell by looking at either the parametric version of this ellipse or the rectangular version of this ellipse that it's got a major axis that's along the y-axis, and that the major axis is 8 units long and the minor axis is 6 units long along the x-axis. Good or no? What about this one? What do you think this should look like? Any ideas? We'll go and graph it in a minute, but first one we did was a parabola. The second one we did was circle. Third one we did was an ellipse. The last one we are going to do here should be what? Yeah, hyperbola makes sense because those are the four conic sections, right? If we were sitting in my classroom, I'd be holding up like these nice little cones and double cones and showing you how we slice them to get all the conic sections, but alas, we can't do that. So can we turn this into the standard form before we even look at the formula for a hyperbola? Any thoughts on how we're going to do that? It's going to be a similar process again. Yeah, we're going to have to square them, but before we square them, we're going to have to do the division like we did with the ellipses, Nick. So we're going to get x over 3, and we're going to square it, is equal to secant squared t. And we're going to have y over 2, we'll square that, is equal to tangent squared t. And then rather than add them together this time, because adding secant squared t plus tangent squared t, that doesn't really give us anything. What's the Pythagorean trig identity that involves secant and tangent, or secant squared and tangent squared? Yeah, 1 plus tangent squared equals secant squared, right? So if 1 plus tangent squared is secant squared, that means that secant squared minus tangent squared is equal to 1. So what we're going to do is we're going to take this one, the one with the secant squared, and we're going to subtract the one with the tangent squared. So we're going to end up with x squared over 9 minus y squared over 4 is equal to secant squared t minus tangent squared t. Or x squared over 9 minus y squared over 4 is equal to 1. And that's our standard form for a hyperbola. So if we go back into Desmos and take a look at this, so what do we have? We had 3 secant t, is that right? And we had 4 tangent t, I think. And there's your hyperbola. So anytime you've got a secant and a tangent in here, it's going to give you a hyperbola. And if we take a look at what, because we know these have asymptotes on them, right? These are how we find the asymptotes for a hyperbola in standard form. So we can also find the asymptotes by converting into this form, or we should be able to note, we ended up with, which one did we end up with? We ended up with x squared minus y squared in ours, or we end up with y squared minus x squared. We got x squared minus y squared. So we had x squared over 9 minus y squared over 4, which means that our asymptote should be y equals plus or minus 2/3 x. And we can see that we can also find those by just taking a look at these 2/3, the 2 divided by the 3 there. And if it's flipped around the other way, it'll just be the opposite. So if we have y squared minus x squared, it's always the value underneath the y divided by the value underneath the b, or underneath the x. Does this all look a little bit familiar too? Back from AIM 3 probably? Hopefully. All right, I want you guys to graph this one real quick while I go deal with my children for a second. Sorry about that. All right. So you guys get a graph of this one or no? You guys graph this or not? Working on it. Okay. Let me know when you guys are all set with that one, and we'll talk about it. Okay, I got one person that says they're done. So I'll assume that means everyone's done. We're only taking our parameter t from 0 to 1 here. So what we want to note is that anytime both the x coordinate is a linear piece, so 4t is a linear piece, and 2 minus t is also linear, anytime they're both linear, the parametric that you end up with at the end is also going to be linear. So all you have to do is find, if they're both linear, the first point, the initial point, we call it, and the terminal point, the last point. So we'll plug in 0. So if we plug in 0, this should give us, we'll say at t equals 0, we'll end up with the point 0, comma 2. And at t equals 1, we end up with the point 4, comma 1, right? So this is all it is. Oh, that's a terrible looking line. Hopefully that's what you ended up with. Is that what you guys got? Any issues with that? So important thing to remember about this is if both pieces are linear pieces, your final result will also be linear. All right, so this one should be pretty straightforward. If we see that both pieces are linear, all we need to do is find the t equals 1 and the t equals 3 values. So at t equals 1, what's x going to be? -1. And at t equals 1, what's y going to be? Should be a 4. So we got the point -1, 4. And at t equals 3, what's our point going to be? -310. So hopefully I counted that right. I can't draw a straight line. There we go. Good? Everybody feel all right about that?
Mr. Bachelor, isn't it between 1 and 3? Not -1?
What?
Wouldn't the parametric equation be between... Wait.
Yeah, we gave, so I gave you, okay, yeah, I gave you 1 to 3, and then when we plug in the 1, we get -1, 4.
Sorry, I got confused.
Oh, that's all right. Everybody good there or no? All right, let's take a look at, we got just a little bit more. We got like 2 more things to do here. I want to see if you guys can figure out a way to write this one, take a minute on your own to do this, try and put this into Cartesian form. I'm not sure. Somebody's unmuted out there that's making weird noises on their thing. So if you're not unmuted, there we go. All right. So see if you can get this one to be a nice Cartesian form here. If you feel like you've got it figured out, let me know in the chat. Or you can just shout it out. That works too. Molly, you've got 2y minus x squared over 4 or 2y minus x squared all over 4? Either way, it's not right. Yeah, Darius, you've got 2 over y minus x squared over 4 equals 1. Is that right? Yeah, that looks good. I might like it to be solved for y, but so Darius, walk us through how you did that. Or does anybody need a little bit more time to try and get to there before I have Darius tell us what he did?
I don't know if my mic's working right now.
Oh yeah, yeah, it's not. I can hardly, I mean, I can understand you, but it doesn't sound very good. All right, we'll have to wait for somebody else then, because I'm gonna make one of you guys do this. All right, Molly, you think you got it? Let us know then.
Okay, we'll see how this goes.
All right, we'll see. I'm just gonna follow along with what you do, so
Okay.
hopefully you're not wrong.
I looked at the Pythagorean identity 1 plus cotangent squared x equals cosecant squared x. So to get cotangent squared of t, I took x equals 2 cotangent t and squared both sides. So I got x squared equals 4 cotangent squared t.
Okay.
And then I know that sine is equal to 1 over cosecant. So I put the other equation in the form of y equals 2 over cosecant squared t.
Okay.
And then I solved the first equation, or not solved it, but I got cotangent squared t on one side. So I had x squared over 4 equals cotangent squared t.
Okay.
And then on the other side, I got cosecant squared t isolated. So then cosecant squared t is equal to 2 over y.
Perfect.
And then I just put what cotangent squared t, or sorry, what cosecant squared t is equal to, and then subtracted cotangent squared t from that, and then set it equal to 1. So
Okay, so you
2y.
said cosecant squared t was equal to 1 plus cotangent squared t?
Yeah.
Like that, okay. And subtract the 1. Like that?
No.
Oh, that's not what you did.
No. Well, I mean, kind of, but then you have to put the, like, I took the Pythagorean identity and I said cosecant squared x minus cotangent squared x equals 1.
Oh, okay, so you did that, all right.
Yeah. And then I just plugged in what I had for cotangent squared and cosecant squared.
I got you, okay. Well, then I can get rid of all that. So you said that cosecant squared minus cotangent squared is equal to 1.
Yeah.
Okay, so you said 2 over y minus x squared over 4 is equal to 1. Yeah,
Yeah.
and can we solve that for y? Should be able to, right? We got 2 over y is equal to 1 plus x squared over 4. And we can make that 4 over 4 and take the reciprocal of both sides, which gives us y is equal to what? What does that give us? Should be 8 over 4 plus x squared. Anybody remember what we called that graph last year? Graphs of that similar nature, of that form? We dealt with them once or twice. Nobody remembers? It's very sad. It's called the Witch of Agnesi. Very exciting. Very exciting. All right, any questions on how we went through that? So anytime we've got these parametrics that are in, in these trig forms, we got to use one of these Pythagorean trig identities generally to try and get them into a standard rectangular form if we need to, make it easier to deal with for us sometimes. So, any questions there? Don't worry, I won't test you on the name of this graph. All right, last thing we're going to do here today, which is probably good because we're running short on time. I want to see if you guys can come up with a parametrization for this line segment that has endpoints at -2, 1, and 3, 5. I don't care what your parameters for t are. You can have it go from t equals 0 to t equals 1, t equals 0 to t equals 10, t equals 7 to t equals 7.1. Doesn't matter to me. See if you can come up with a parametrization for that line segment. probably easiest if you use some simple t values like 0 and 1. But so take a couple minutes and see if you can figure that out, and then we'll go through it, and then we'll be done for the day. Anybody feel like they're doing all right with this? Or anybody floundering with no clue what to do? How should I get started with this? Let's say at t equals 0. Anybody have a good idea on how to start? You guys still there? All right. So Molly, how'd you start? Okay, Adrian's got something for us. All right, make an equation for x in terms of x, which yields -2 at t equals 0. Okay, so and Ryan's got just a full answer for us. I like that. Going from 0 to 2. So if we're going to start at 0, we know that the x equation needs to be something, let's call it a times t, and then we need to subtract 2 from it, right? It's not going to matter what that a value is because t is going to be 0. And we know that y is going to equal some other value, b times t, and we need to add 1 to it. Everybody agree with that, that at t equals 0, those equations will both work? So we just need to figure out what a and b are to make it work for our last point. So Ryan looks like he used t equals 2 as your ending point. Or Kiana used t equals 1 as your ending point. So let's say we did it with t equals 1, because I think that's going to make the arithmetic a little bit easier. And then we'll check and make sure Ryan's works for t equals 2 also. So if we use t equals 1, that's going to give us x needs to equal a minus 2, right? A times our 1 minus our 2. So we got to figure out what value for a is going to work out there. And we're going to do y equals our b value times 1 plus our 1. And this has got to equal 3. And this has got to equal 5. And so in this case, a is going to have to equal 3. A is going to have to equal 5. And b is going to have to equal 4. And so we just go and throw those back in over here to give us x is equal to 5t minus 2. Y is equal to 4t plus 1 for t less than or equal to 1, greater than or equal to 0. Does that make sense to everybody? Cool. And we don't need to we don't need to go back in and do it for t equals 2. But if we did it for t equals 2, then these would just be 2's here. So we have 2a minus 2 and 2b plus 1 needs to equal 3 and 5, and we'd solve for a and b that way. We could do it for any ending value of t. Any questions on that? Any questions on anything polar or parametric before I let you guys go? Wow, and we're going to be early getting out of here today, like a full 5 minutes maybe. Look at that. Everyone good? All right, cool. If you have any other questions, just send me remind messages and all that. I'll put up some basic parametric stuff tonight sometime, and I'm not going to grade the parametric stuff either. And then we're going to start talking about limits. We're going to really quickly fly through the basics of limits, and then we're going to get into some a couple of things that we didn't really talk about last year when we did with limits eventually. But most of the limit stuff should be pretty quick, easy review of what you learned in your last calc class. So other than that, have a good day. Go to your next class, do stuff. Oh, Nick's got a question. Yeah, so Nick, if you do a hyperbola, yeah, you should be telling me whether it's opening horizontally or opening vertically. Yep. Luke, we're not going to do limits on a polar graph exactly, but what we're going to do is we're going to do a couple of limits that involve using substitutions to turn things into polar coordinates to simplify them a little bit. So we're not specifically doing the limits on polar graphs, but using the idea of polar functions to help us evaluate some other limits. Any other questions? All right. Let's see here. I can stop this and stop this recording maybe.